All right, hello class. When we last left off, actually in our face-to-face class, we were looking at chapter 2 and specifically section 2.2, which is the limit of a sequence. And we talked about the distance definition, is what I called it, which is that a sequence AN converges to A if, and only if since it's the definition, if for all epsilon greater than 0 there exists an n in the natural such that for n greater than or equal to this capital N we have that the distance between AN and A is less than epsilon. Alright, so we did sort of break down what this definition was saying with an example. All right. I want to also give an explanation of what's considered the topological definition or the set-based definition. So what this definition is basically saying is that if I were to look at, say, a particular sequence and I were to graph it, okay, so let's say that this sequence is converging to 0 eventually. Okay, so here's my ANs. And what this definition is basically telling us is that for any epsilon I choose, so if I choose, let's say this is epsilon equal to 1, well, at some point, every term past a goalpost, I always call this in the goalpost. All right. So there's a point if AN is converging to 0 in this case, then for every epsilon we choose, we should be able to find an n such that everything past it is going to get our distance between these two things less than epsilon. So here's the limit, 0, and it looks like everything past this particular value here. Okay, so n here I could choose to be 3. Oops. So everything past 3, all the terms of my sequence are shrinking to 0. Okay, so then if I choose another epsilon, let's say I choose an epsilon 2 to be 1/2. So all right, so our n can't be 3 because it looks like these two guys hit the epsilon, which that's not that big of a deal. But then notice in the next step we jump above the given tolerance, the given epsilon, and then we shrink back down again. But our n's not going to be here because eventually we leave this epsilon tolerance again. And then here, it looks like if we were to choose our next n to be this value, everything past it seems to be within this epsilon tolerance. Okay? So we couldn't say it was true here, but everything past here will be within the tolerance. And then we could maybe choose an even smaller epsilon. Okay, so here we get one term within the epsilon tolerance, but that's not our goalpost. That's not our n because we have terms that still leave it. But then, so it looks like maybe here would be our next n. So I didn't give this one a number here. That would be n2, and then this might be our n3. And so if our sequence is actually converging to 0, like we say, then we can always, for any epsilon, for any tolerance we might want, say this was 1/4, however small of an epsilon we choose, we have to be able to find a point where everything past that point will be in that epsilon tolerance. I like to use the word tolerance. Okay. Now there's another way to define this. So this is, like I said, the distance definition. We're talking about the distance, but between the terms of the sequence and its limit, and those are shrinking down to the distances are shrinking down to 0 the further out we go. Okay. In other words, we should be able to find a point where everything past that point is going to be within whatever tiny epsilon we choose. There's another definition that explains this in terms of sets and what's called epsilon neighborhoods. So in this particular lecture, I want to give those definitions, explain them, and then start looking at some examples and proofs of this stuff. All right, so to get going on this definition, or this set definition for convergence of a sequence, we need a definition of what's called an epsilon neighborhood. Okay, so given a real number a and a positive number epsilon greater than 0, okay, the set, which we call v sub epsilon of a, so it almost looks like a function here. Okay, it's going to be the set of all x in the reals such that the distance between x and a is less than epsilon. Okay, what this set ends up being is actually an open interval. It'll be a minus epsilon to a plus epsilon. Okay, that's what this v sub epsilon, or this epsilon neighborhood, ends up being. And as we see here in this next step, is called the epsilon neighborhood of a. Sometimes you could call it around a. And if we wanted to, say, draw a picture of this, so let's say we're on a number line, okay, and say a is here. Now what the epsilon neighborhood is we go out epsilon units on both sides. Okay, so that makes this a plus epsilon, and that makes this a minus epsilon. Okay, so we're talking about this open interval here. So this set here is v sub epsilon around a, or the epsilon neighborhood around a. Okay, and so what how we approach this, how we use this to talk about the convergence of a sequence. So instead of saying that the distances get smaller and smaller, or that we can find a goalpost where every term, the distance between it and the limit are within epsilon, what we can do instead is say, oh, well, for every epsilon, there's a point where every term after an n will be within the epsilon neighborhood. Okay, so let me throw out the definition there, and I'll draw a picture and we'll look at an example. All right, so here's the definition, the convergence of a sequence. I call this the set definition, but this is officially known as the topological version. In most cases, the topological version of definitions usually involves sets. Okay, so if you ever hear that something is a topological version or topological definition, it's usually given to you in terms of sets. A lot of analysis is done in terms of distances. So you could think of the first definition as sort of the analytical definition, while this is the topological one. Anyway, that's neither here nor there. So here it goes. It's a sequence, a n converges to a, if and only if, given any epsilon neighborhood, v epsilon a of a, there exists a capital N in the naturals such that a sub n is in the epsilon neighborhood for all n greater than or equal to this capital N. All right, so let's talk about what this is saying. So instead of graphing our sequence as we did before, where I had a y-axis and I was sort of measuring the height versus n, an n-axis, what I'm going to do instead is just say here's my A, and if an converges to A, then what I'm going to do is start plotting the terms of A just on the number line. Okay, so let me pick an epsilon. So just pick an epsilon. Okay, and let's say I have A1 here and A2 here, and I've got A3 here, and maybe A4 is here, and maybe A5 jumps back here. But eventually, okay, since AN is converging to A, eventually every term of the sequence past a certain point needs to be in this set. So maybe A6 jumps in here, but maybe A7 jumps back out, but then A8, then A9, A10, and then every other term of the sequence ends up being in here because it eventually converges to A. So this was supposed to be an A9 here. So basically everything past 8 is going to be in the epsilon neighborhood. So our n here would be 8. So AN is in this V epsilon of A. Okay, and this will be true for all in past 8. Okay, so 9, 10, 11, 100, a million, everything past it. And then if I pick a smaller epsilon, say I pick a smaller epsilon here, well, once again, there's going to be a certain point where every term past that point will be in this epsilon neighborhood, and then in this epsilon neighborhood, and you can get it smaller and smaller and smaller. And if the sequence converges to that value, then this has to happen. Okay, so last time we looked at a sequence 1 over square root of n, I believe it was. Let's look at another sequence and approach it with this topological definition instead. All right, so here is the claim that this sequence 1 over n squared goes to 0. It converges to 0. Okay, so I'm going to start by letting epsilon 1 equal 1. So we're going to start by looking at epsilon equal to 1. Okay, so here's the question. Can we find an n such that 1 over n squared is in the epsilon neighborhood around 0 for all n greater than or equal to this capital N? Right, well, this epsilon neighborhood, that's actually, our epsilon is 1. So V1 of 0, that is going to be the open set -1 to 1. Okay, so let's check some values here. Again, this is not how we would approach this all the time. This is just to get an understanding. Okay, so when n is equal to 1, we get 1 over 1 squared, which is 1. Okay, that's not in -1 to 1. But how about n equals 2? Well, if when n equals 2, we get 1/4, and that will be n negative 1 to 1. So that works just fine. So that works, and then our next n will be 3, which will give us 1/9. So 1 over n will be in this set negative 1 to 1, basically for all n strictly greater than 1. So our capital N needs to be strictly greater than 1. So the answer, of course, is yes. Choose capital N strictly greater than 1. Okay, well now let's go a step further. Let's let epsilon, let's say the next epsilon we look at. Let me just all right, so now let's say that our next epsilon is 1/10. So the question then is, can we find an n such that 1 over n squared is in the epsilon neighborhood with, sometimes this is called the radius, the epsilon neighborhood of radius, or the 1/10 neighborhood around 0 to 1. So this is actually the open set negative 0.1 to 0.1, or negative 1/10 to 1/10. Okay, so, and that, and we find this capital N such that this is in there for all n greater than or equal to that capital N. Well, let's see. If we check different values, n equals 1, of course we get 1 over n squared is 1. For n equals 2, 1 over the 2 squared would be 1/4. So 1 is definitely not in negative 0.1 to 0.1. 1/4 is not in negative 0.1 to 0.1. All right, then n equals 3. That will give us 1 over 3 squared, so that's 1 over 9. So that's not in negative 0.1 to 0.1, but we're close. All right, so then how about n equals 4? We'll get 1 over 4 squared, which will be 1/16, so that will be in negative 0.1 to 0.1, and then every value after that should also be in that set. So these guys don't work, but this one does. Okay, so really, as long as we pick a capital N greater than 3, then 1 over n squared will be in negative 0.1 to 0.1 for all n greater than or equal to this capital N. All right. Now let's just keep this going. Let's go to a next step to, let's say our third epsilon is 1 over 100. All right, so can we find an n? We want 1 over n squared in the epsilon neighborhood around 0 with epsilon equal to 1 over 100. So this is the open set negative 1 over 100 to 1 over 100. Now I'm not going to check a bunch of values because I'm just going to make an educated guess that, well, when n is 10, 1 over n squared will be 1 over 10 squared, which is 1 over 100. Now that will not be in this set, since remember these are open intervals. However, everything past this value should be. All right, so n equals 11. 1 over n squared will end up being 1 over 121, and that will be in this set. All right, so choose capital N strictly greater than 10. And then 1 over n squared will be in v.01 around 0 for all n greater than or equal to capital N. All right, so the answer is yes, given any n, we should be, or sorry, given any epsilon, we should be able to find a capital N such that everything past that point, okay, will give us what we want, will get us in that set. So now, here's where we really, where the work really comes. For any general epsilon greater than 0, can we find an n okay, such that 1 over n squared is in the epsilon neighborhood around 0 for all little n greater than or equal to this big N. Okay, so here's what we want. We want 1 over n squared in this open set. So it's 0 minus epsilon, so negative epsilon, to 0 plus epsilon, which is just plus epsilon. Well, by definition, this implies that we want 1 over n squared between negative epsilon and positive epsilon. All right, and actually I'm going to sort of ignore, I'm going to ignore this part and just focus on this part. Okay, so this is what we want. And if I sort of move these things around, right, move the n squared over and the epsilon over, you'll get 1 over epsilon is less than n squared. When you take the square root of both sides, you'll get 1 over square root of epsilon less than n. And there we go. The answer is yes. Okay, I'll write it over here. Yes. Choosing capital N greater than 1 over the square root of epsilon will give us 1 over n squared in the epsilon neighborhood around 0 for every little n greater than or equal to big N. So notice what I did here. I just found what it was I wanted and played with it until I essentially solved for n until I got this. So as long as all my n's, and it's kind of off the screen here, as long as all my n's are greater than this 1 over square root of epsilon, we're in business. All right, we're good to go. All right, so let's actually turn this into a proof. Okay, so we will do that once I clear the screen here. All right, so here's our prompt. We want to prove that the sequence 1 over n squared converges to 0. All right, so proof. All right, here's how they always start. We're going to let epsilon be greater than 0 and choose, hopefully there's some construction going on next door. Hopefully you can't hear that. So, sorry. But choose capital N to be greater than 1 over the square root of epsilon. And here's where here's where the books can be frustrating, because it looks like this came out of nowhere, right? However, you just saw where we got this number from. Okay, that was the scratch work. So usually when you see proofs of this kind, that's what they're doing. They just don't show that part. They just pick an epsilon, sort of. It looks like out of thin air, but there is work there. Now, I will show you a way that you can get around that and write a formal proof, without needing to know this part right off the bat. But anyway, so we're going to choose capital N greater than 1 over the square root of epsilon. Then, for n greater than or equal to capital N, we have that our little n must also be greater than 1 over the square root of epsilon. Okay, now this implies that, well, if we square both sides, we'll get that n squared is strictly greater than 1 over epsilon. Okay, which then implies, well, we're going to move some things around. So this implies that move this epsilon over, this n squared over, and I'll get that epsilon is greater than 1 over n squared. Okay, and this 1 over n squared is positive, which will be greater than negative epsilon. So this implies that 1 over n squared is in the open interval negative epsilon to epsilon, which is v epsilon around 0. And that's actually it. So for every epsilon, we found an n such that 1 over n squared is in the epsilon neighborhood. So for all epsilon greater than 0, there exists an n such that 1 over n squared is in the epsilon neighborhood around 0 for all n greater than or equal to this capital N. So 1 over n squared converges to 0. All right, so now that we've proved this, one thing I want to show is once we get to this point here, we can actually prove this with the other definition. Okay, so this is what we're doing here is the set version of the definition. Let me show you how we would prove this with the distance definition, and that's typically how it's done instead. Okay, so I've cleared away that last part of the proof. Now that we're here, what I can do is take this, and then this implies that the absolute value of 1 over n squared is less than epsilon, which is the same thing as saying that the absolute value of 1 over n squared minus 0 is less than epsilon. And once again, this implies that the sequence converges. Okay, same reasoning, because for every epsilon we can find an n, capital N, such that for all little n greater than or equal to that capital N, we get this, that the distance between the 1 over n squared and the limit is less than that epsilon. All right, so let's look at proving the one we looked at last week, which was 1 over the square root of n. All right, so we want to prove that 1 over the square root of n converges to 0. All right, so what we're going to do, if you don't remember what we did the last time in class, you don't have your notes handy, remember this is what we want. We want 1 over the square root of n minus 0, absolute value to be less than epsilon. So this thing's positive, and so we can simplify this to be 1 over the square root of n less than epsilon. So this is what we want. All right, now I'm going to square both sides because I'll get 1 over n is less than epsilon squared. Then move these things around. I'll get 1 over epsilon squared is less than n. Okay, there we go. So the capital N we choose, we're going to choose capital N greater than 1 over epsilon squared. All right, so that's where this comes from when we do the proof here. So when we write up our proof formally, proof, okay, you always start with let epsilon be greater than 0. Okay, and this is what some people call the backwards reasoning. I don't know if I'd call it that. We are going to kind of trace this backwards, though. So we're going to let epsilon be greater than 0, and we're going to choose capital N greater than 1 over epsilon squared. Now, notice there are a few things going on in this statement. I didn't mention it last time, but this line right here is actually implying or evoking a lot of things. For one, we are using the fact that epsilon is not equal to 0 so that we could divide by it. And we can always choose a capital N greater than this 1 over epsilon squared. This is by the Archimedean property. Okay, so every time we do this, we're actually invoking the Archimedean property, which we prove directly from the axiom of completeness. So this is basically a direct result of the axiom of completeness. Just wanted to verify that. All right, so we've chosen our n such that it's greater than 1 over epsilon squared. So for any n greater than or equal to capital N, we have that little n is going to be strictly greater than 1 over epsilon squared, which means that, and now I'm going to kind of just reverse this. This tells me that epsilon squared is greater than 1 over n. Now everything's positive here, so I can take the square root of both sides to get that. Tells me that epsilon is greater than 1 over square root of n, which implies that the absolute value of 1 over the square root of n minus 0 is less than epsilon. Okay, so this proves it for us. So for all epsilon greater than 0, there exists a capital N in the naturals such that n greater than or equal to this capital N yields 1 over the square root of n minus 0 is strictly less than epsilon. Okay. Notice I use the distance proof here. If I wanted to, after this step, so let's call this step star, just to give you an idea of how it works, from star, we have that epsilon is greater than 1 over the square root of n. And 1 over square root of n is always positive, which will be greater than, say, negative epsilon. All right, so this implies that 1 over square root of n is in the set negative epsilon to epsilon, which is the epsilon neighborhood around 0. Okay, so for all epsilon greater than 0, there exists a capital N in the naturals such that 1 over the square root of n is in the epsilon neighborhood around 0 for all n greater than or equal to capital N. All right, so that is the other way you could complete this proof using that topological definition. Okay. All right, so let's prove that the sequence n plus 1 all over 2n converges to 1/2. So this one will be a little more involved, but still follows the same idea. So what I'm going to use the distance definition. That's the more typical one. But every so often the topological one's a little more handy. So here's what we want. We want the distance between n plus 1 over 2n and 1/2 to be less than epsilon. And specifically, when you want to find n's, or we want to find a capital N where everything past this will happen. Okay, so I'm going to simplify the inside of this absolute value. So I'm going to do the fraction arithmetic here. I'll get 2n plus 1. So I'm going to do the cross multiplication thing. Minus 2n all over 4n. And we want this less than epsilon. And I'm going to simplify this a bit. I'm going to do 2n plus 2 minus 2n, and the 2n's cancel. Perfect. All over 4n. I don't know why I switched colors there. So I'm going to have 2 over 4n, so this will be the absolute value of 1 over 2n. And this will always be positive because n is in the naturals. So really we have this, 1 over 2n less than epsilon. And now we mess with this. I'm going to leave the 2 here, but I'll move n up and epsilon over. So I have 1 over 2 epsilon is less than n. And there we go. That's the capital N I'm looking for. All right, so now that I've found it, now I can actually write the formal proof. All right, proof. We're going to let epsilon be greater than 0, and then choose capital N in the naturals. I didn't put this part last time. I often don't. I usually have a soft assumption that n is in the naturals. Anyway, so we're going to choose n in the naturals where n is strictly greater than 1 over 2 epsilon. Right? And we can do this, 1, because we know epsilon's positive, so we're not dividing by 0 here. And 2, using the Archimedean property, we can always find an n that does this. Okay, so then, for all little n greater than capital N, we have that little n is greater than 1 over 2 epsilon, and we just kind of work backwards through what we've already done. Okay, so that's one nice thing about these proofs is you just kind of go backwards through your work. So that is why some people call this backwards reasoning. But, I'm not a huge fan of that term. Anyway, so I'll switch this around and get that we'll have 2n. Whoops, no, I don't want to do that. I want to say that this gives me that epsilon is greater than 1 over 2n. All right, now you might feel a little odd about working backwards through these steps here, right? You would have to say introduce a 2 and all this stuff. So let me show you what you can do. So let's end our statement here. Okay, then we also have, or let me say instead of that, then I'll do this. The absolute value of n plus 1 over 2n minus 1/2, okay, is equal to, now I'll do the simplification, which is the 2n plus 2 minus 2n. Notice I'm kind of skipping a little bit here, which will be equal to 1 over 2n, which will be less than epsilon by basically the statement we already have here. Okay, so therefore n plus 1 all over 2n converges to 1/2. All right, so notice I didn't do the full backwards reasoning, and that's sort of why I don't particularly use it, because sometimes going exactly reverse through your work will seem kind of awkward. So sometimes I do a little bit here to get this, and then I mess with what I'm actually looking for, because remember, we want this thing less than epsilon. All right, the last thing I want to talk about, and in the last minutes I have of this particular lecture, is to say that a sequence that does not converge is said to diverge. All right, so that, I don't think there's much new there, but let's look at an example. Consider this sequence that does this. Let's say it does like 1/2, negative 1/2, 1/2, negative 1/2, 1/2, negative 1/2, 1/2, negative 1/2, and it just repeats that process over and over again. Okay, so here's my argument. Let's say that this is the sequence an. So here's my claim. An does not converge to 1/2. Well, why might that be? Well, if we take a look at this on a graph where I'm plotting the ANs on the y-axis and n on the x-axis, what ends up happening is basically it jumps back and forth. We have 1/2, negative 1/2, 1/2, negative 1/2, 1/2, negative 1/2, 1/2, negative 1/2. Well, if I say that an converges to 1/2, that means for every epsilon that I choose, the distance between all the terms, at some point, all the terms should be within epsilon of the limit. So if this is 1/2, well, if I pick an epsilon, say, equal to 1/2, right? So here's my tolerance. I'll never be able to pick an n, right? I'll never be able to find an n, because if I say this is my n, well, guess what? There's an infinite number of terms that aren't within this epsilon tolerance. I can't pick this n or this n. I can't pick any n, because no matter what I do, there will be an infinite number of negative 1/2 that live outside of this epsilon tolerance. Okay? And we can do the same thing for negative 1/2. So actually, this sequence does not converge to plus or minus 1/2. It does not converge to anything. So AN diverges. Now, we're not going to do many, well, right now we're not going to do many proofs proving that something diverges unless it's just completely obvious. We're going to have a criterion that we can apply as we move forward to do that. Okay, so I'm going to leave it there, and I will catch you all in the next one. Cheers.